All right, section 3.7 is changes of state. And a change of state is defined as when either a substance converts from a solid to a liquid, and that would be in melting, or a solid is converting to a gas, which would be sublimation, or a liquid is converting to a solid, that would be freezing, or a liquid converts to a gas, which is boiling, or a gas converts to a liquid, which is condensation, or a gas converts into a solid, which is called deposition. And you can see all of those top ideas in this diagram on the right. You have the solid on the bottom left, which is ice in this case. You've got the liquid at the bottom right, and the gas at the top of the triangle there, which would be steam. The names for each of these phase changes are listed in this table. I mentioned them in the last slide. The picture on the last slide shows the names as well, but if you want it in a table form, they're right here for you. So again, solid converting to a liquid is melting, solid converting to a gas is sublimation, liquid converting to a solid is freezing, liquid converting to a gas is boiling, gas converting to a solid is deposition, and a gas converting to a liquid is condensation. These pictures here are of my car, and you can just see the differences between condensation and deposition. So when it's not raining, but like you wake up in the morning and there is water on your car, that's due to condensation. Basically, the metal on the car gets cold enough that it gets below what is the dew point, and so it actually sucks water from the air onto its surface, and it condenses into the liquid state. You can also see that anytime you have a cup of ice water on the outside of the cup, it's not raining onto the cup, which you call precipitation, which is something different in chemistry, by the way. But it's just water from the air in the vapor form hitting the cold glass and condensing into a liquid. On the right here is deposition. So if you were to take a glass and put it into the freezer, which you may have done before because people like to do that for their glasses of beer or whatever, you'll notice that there is going to be ice on the outside and even on the inside of the glass, which is supposed to be kept empty. The water that's inside your freezer doesn't first go into the liquid state. It does not condense first, because look at the droplets on here. It doesn't do that and then freeze. It just goes from the vapor state in there directly to the solid state, because the glass gets cold enough to freeze it instantly. And so I have this picture of my car. It's the same thing. If you wake up in the winter and it's well below freezing, you'll see what we call frost on the car or on your windows and stuff. That's not directly going from gas to liquid and then liquid to solid. It's just gas into solid. That's called deposition. It's like it deposits onto a surface. The melting point is defined as the temperature at which a solid will spontaneously convert into a liquid. The freezing point of a substance is the reverse of the melting point. It's the temperature at which a liquid will freeze into a solid. And the boiling point of a substance is the temperature at which a liquid will spontaneously convert into a gas. The heat of fusion of a substance is the amount of heat required to completely convert 1 gram of a solid substance into the liquid phase once the substance has reached the melting point. And this is the in this process, the temperature and pressure of that substance, or the atmosphere around it, the pressure of it, will remain constant. So you may notice that if you are if you put ice in water in your cup, if you put a thermometer in there, you'll see that the temperature will say 0 degrees Celsius or 32 degrees Fahrenheit. The ice, in order to get it to be a solid ice in your freezer, has to be below 0. Okay? The water can be whatever temperature it is, above 0 and below 100 degrees Celsius. But when you mix the two together in that cup, they will equilibrate to 0 degrees Celsius. And you can keep your thermometer in there for the whole time from which it reaches 0 degrees Celsius and all of the ice melts. The temperature will still remain at 0 that whole time. As that ice is melting, the temperature of the entire mixture stays the same at 0 degrees Celsius.
At the freezing point of a pure liquid, a dynamic equilibrium is established between molecules in the liquid phase and molecules in the solid.
Evaporation occurs to a liquid substance when two conditions are met. The system that it is in is open, and the particles in that substance that's a liquid have enough energy to evaporate and be in the liquid phase, the gas phase. They have enough energy to be in the gas phase, and they have to be at the surface of the liquid. So you can obviously tell the difference between when evaporation is occurring and when boiling is occurring, because the evaporation only occurs at the surface, which is why you never see bubbles occurring. Boiling happens throughout the entire sample of a substance. At the bottom, in the left, in the middle, in the right, in the center, tops, corners, and all those things. If all of those pieces of, let's say, water in all proportions would be 100 degrees Celsius, they have enough energy to change, so those bubbles form everywhere in there, and they escape. The quote-unquote air inside those bubbles, by the way, is water vapor. It's not air. It's just water vapor, because it's going from a liquid state to a gas state and coming out of that solution. The heat of vaporization is defined as the amount of heat required to convert 1 gram of a liquid substance at its boiling point to the vapor phase. And just like with the heat of fusion, the heat of vaporization will not change the temperature or the pressure. So if you take water and you boil it, you can put a thermometer in there. The entire time it's boiling, it's going to stay at 100 degrees Celsius, even though you're adding more energy. Like if you're boiling a pot of water to do spaghetti or something, once it's boiling, the water temperature is 100 degrees Celsius. But you have to keep heating it at hundreds of degrees, at least 100, but the fire in a gas stove is over 100. You're continuing to heat with this really high temperature flame, and it's still staying at 100 degrees Celsius. The heat of vaporization is the amount of energy required to convert just 1 gram of it all the way from liquid to gas. And you could do calculations like, hey, I've got a whole pot of it that weighs 3 kilograms. How much energy is that going to take to heat it up to boiling and get all of it to be in the gas phase? We're not going to do that, but you could do that.
At the boiling point of a pure liquid, a dynamic equilibrium is established between molecules in the liquid phase and molecules in the vapor phase. Some molecules at the surface of the liquid have enough energy to leave the surface and enter the vapor phase. Some molecules in the vapor phase collide with the surface. At equilibrium, the number of molecules leaving the surface is balanced by the number of vapor molecules that...
This picture from your book just shows how water changes temperature. It's got 50 degrees Celsius on the left, and then on the right, once it's reached boiling, it's got 100 degrees Celsius right there. And it would stay at that, as I just mentioned, until all of the water has boiled. This picture just shows that the sublimation versus deposition. you have to add heat to the solid to get it to convert to a gas. Dry ice does this, and it goes, let's say it's CO2, that's a solid, it's going to go into CO2, that's a gas, and it can go backwards as well. This happens at about negative 76 degrees Celsius. So if you go to the store and you buy dry ice, it's going to sublime at negative 76 degrees Celsius or above. Obviously, the temperature in your house or outside or whatever room you're in is going to be above negative 76 degrees Celsius, so it will spontaneously sublime. But if you put something in there that's not water, because water freezes at 0, if you put something that freezes below 76, you can get that liquid, like acetone, for example, you can get it to negative 76 degrees Celsius, which is incredibly cold, obviously. This here is a heating curve, and it's a graph of the temperature of a substance versus the amount of heat added. I mentioned earlier that solids take less energy to heat them up per gram than do the corresponding liquids, and we can see that in this graph. If you look really closely here, you can see the change in temperature of the solid goes up. It's really steep change, so it takes very little energy to change it from a solid to the melting point. So you can see here that going from the solid to the liquid only changed the temperature, or I should say it only required a tiny bit of heat. This is your delta Q from 0 to that point right there. But once the substance is a liquid, it takes this much energy to convert it, a lot bigger. And then if you actually look at the gas at the far right, it's a very steep curve as well. So it takes very little energy to heat up gases. It takes very little energy to heat up solids. It takes a lot more energy to heat up a liquid. But all in all, if you look at the whole thing, at the phase transitions, the temperature does not change. It stays the same. So as we can see here, once you get that solid up to its melting point, it stays at 0 degrees Celsius. Once you take that water and you reach its boiling point, its temperature stays the same for a very long time. I'm sure you're all aware of how long it takes to boil water. It just takes so long. The reasons behind all these things are not necessarily for the scope of this class. Like, why does a solid heat up faster than the liquid or the gas? Why does the gas heat up quicker than the liquid? And why does the boiling take so long compared to melting? Those are reasons that can be explained, but it's not for the scope of this class, so you don't need to worry about it. Right here is a cooling curve, and it's a graph of the amount of temperature of a substance versus the amount of heat removed. So it's the exact opposite of previous, which really just makes it useless because they're the same thing. It's just the inverse of it. So it's heat removed versus heat added, but you can see the same thing. The temperature of the steam goes down very quickly. The temperature of the ice goes down very quickly. But the temperature of the liquid water is much slower to cool down than the others. Either way, again, the temperature will stay constant at these equilibria where it is condensing into a liquid or freezing into ice. And that is it for chapter 3. Here's the list of all the key terms that we went over throughout this chapter that you need to know for your test. If you have any questions, if you need any help, please come see me in my office hours, email me, or whatever you need to do. Again, these are problems you should work on. Also, check and do your homework assignments. and do them. Doing all of this should prepare you definitely well enough for your test. Good luck on your test, and I'll see you in the next lecture.